Okay, let us look at this another differential equation. So it's part of the equation that we have to solve in our math 3 as well, this one here. So this one is a homogeneous differential equation. So we just from the exacts, which have a general form, which are the standard form, xy dx plus n xy dy is equal to 0. So this was the standard form for the exact differential equation. So there is a differential equation. They have the same structure. So the homogeneous differential also have this same structure as well. But of course, sometimes it depends on the book you are using. Okay, I will show you what I'm talking about that. Let us first just focus on this one. So with the exact differential, what we have with these two functions here, we looked at these ones as being partial derivative of some f of xy function. So m being then a partial derivative with respect to x, and the n being a partial derivative with respect to y. So for the homogeneous differential equation, these ones are no longer partial derivative, but they are functions. They are homogeneous functions. Okay, they are homogeneous functions, and they must be homogeneous function of the same degree. Okay, of the same degree. Okay, so let me just aside here, maybe say write a line, and I say what is a homogeneous function. Maybe if you can look at that first. Homogeneous function. So how do we tell if a function is homogeneous? So let us say we have our function here. Say we have f of x, y. This is a function. So this function here will be homogeneous only if it satisfies, a certain condition. So what is that condition? I will say, and let me put it like this. Let me say then. Let me put it like this. I think you will understand. Let me say then, f of x is a homogeneous is a homogeneous function if f of tx ty is equal to t raised to n f of xy. This is just a general statement that this function here is a homogeneous function if we are able to do this test into this function. And if we were able to do this, then what happens is that n gives the degree of the function. So m is the degree of this function here. Is the degree of, let me say, f of xy. It means it's a homogeneous function of second degree, is a homogeneous function of third degree, so like that. Maybe if I can give you an example, just one example. Let us have a function here, f of xy is equal to, maybe say what, is equal to 3 x squared plus y squared sine y over x. Then let us check if this function is homogeneous function or not. So how do we check? So we check by replacing x with a tx. We replace y. We replace y with a ty. So therefore, in our test, therefore we'll have tx, ty. Therefore, this will be 3. So we have x squared, therefore we have tx squared. Plus we have y squared, therefore it's a ty squared. Sine, we have y, therefore it means it's a ty. We'll have x, therefore means it's a tx. Okay, so this is what we have. Now our hope is to have t being a common variable in all the term, and it must be the same power, because otherwise when we try to pull it outside, then we can take out maybe say power 2, but if there's power 3, for instance, in one of the terms, then that power 3 will be stuck with some t variable. Okay, so therefore this is a t squared times x squared, means it's a t squared, y squared, sine. So here you can see they will cancel, the t on top, t below, they will cancel, they will then give us x over y. Okay, so while we try to pull it outside as a common value, but when they divide like this and they give us 1, it's perfectly fine, it's acceptable, just like in y over x here. The idea is that we must have f of x, y only left inside here. There mustn't be any y somewhere. Okay, so therefore having t squared is common, we can see that. Then the first term will be left with a 3x squared, plus second term will be y squared sine y over x, close the brackets. So what we see here is that this that we have down here, this that we have down here is exactly the original f of xy that we started with. So it therefore means we can, for instance, therefore write this as f of xy, because we can see it's the same thing. So what have just happened? We started with f of t xy, but when we get here, the t is now sitting alone next to the f of xy here, and is sitting alone with the power 2. This is very special. It tells us that this original f of x that we are working with here, it means it's a homogeneous function of second degree. So this is the degree, this one, this 2. Right. So this is how we conducted this test. Let us say we have a function here which is equal to maybe say 3xy plus y cubed. Then we try to test if this function is homogeneous or not. So what we do, the same test, we must replace x with a tx, replace y with a ty. So when there is x, we put a tx. When there is y, we put a ty. Plus ty cubed. So this will therefore be 3. So it means it will be t squared x and y. Therefore plus t cubed y cubed. This will be t squared 3xy. Power 2 is outside, it means we're left with a t here, y cubed. So what do you see here? What you see here is that we come into a problem. There's a t that is left inside here, which we don't know what you can do with it. It's just forever stuck inside there. And then what it therefore means here, it therefore means this f of xy function that we're trying to test if it's a homogeneous or is not a homogeneous. It means this f of xy that we have here is not a homogeneous function. Okay, so it means it's not a homogeneous function. Okay, so in this differential equation that you are working with, so this could be your m value or your n value. This could be your m or your n function, because we're having two functions there, which is m and n. And then we have to perform this test, exactly the same test that you have here. You have to perform it in both of these m and x, just as you did cross differentiate previously. Now we have to check if they are homogeneous functions, and if they are homogeneous, are they of the same degree? They must be of the same degree. And then if it's true they are of the same degree, then it means we have a homogeneous function, so we have a homogeneous differential equation that we can solve using separation of variables. Right, so now the question is, how do you solve? Okay, so the first thing, of course, you must have standard form. It's key, it's important, you must have it, so that you are able to figure out your n value, sorry, your m value, and also your n there. So you must be able to figure them out. But maybe if I may go back to what I said previously, that sometimes it also depends on the book you are using. I know there are some places where they will put this differential as follows. Let me raise and write it here. So they will put it as dy over dx is equal to f of xy. There's a general structure for these differential equations. Okay, so there are places where you find that they put it like this, and then when you have to then test if it's a homogeneous differential here, then they will tell you that, we must substitute this one, and then you must get f of x, y. Okay, so the reason being, what you have here, we have a t0, so therefore you just get f of xy here, which is fine. In fact, myself, I'm very okay with it, because also when we have to solve this equation, even though we may start with this, according to the material also we are using, but what happens is that when we start solving, we go into this, then we start substituting our y, v of x, then we continue afterwards. Okay, so let us come back in this situation, what we have here. So when we solve these ones, then let me write steps. There's not so many, I think it's just a 2 or 3. Of course, the entry into these steps is the standard form. You have a standard form first, then step number 1, what do you do? Of the two equations, homogeneous and exact, you may be confused which method to use, so it's best to do the test. So the kind of a test that you have to do, you have to check, let me say, check if homogeneous ODE. Check if homogeneous ODE. I think it's enough, we can understand it. Check if you are having a homogeneous ODE. So how do you perform the test? I'll say check if the given equation is a homogeneous ODE. In fact, let me write like that. I think it will be better. Check if the ODE is a homogeneous ODE. Right. So how do we check for that? We have to substitute. You have to substitute. Where there is x, you put tx. Where there is y, you put ty. This you do in both m and n. Right? So in m, if this is a homogeneous differential equation, you must be able to say, if we had just substituted your tx and a ty, you must get t. I'll use a p because we also used the same in class. Then get back your m value, your m function. Also in n, if you had substitute tx, ty, you must get back your t. Let me say q, then xy. So if this is the case, it therefore means both m and n, they are homogeneous function of p and q degrees. And then what is important is that if p is equal to q, we have something special here, because p is equal to q, it implies we're having a homogeneous ODE that you can solve using these steps that we then put next. Okay? That we can solve using the steps that we put next. So step number 2, what do? You substitute y is equal to v of x. Then, of course, you are now having new variables. You must therefore find the dy with respect to x, which is equal to v plus x dv over dx. After I've done this substitution, we've simplified your equation. Then what you do next, you solve for v of x, right? Solve for v of x. After you have your v of x, since this is not the original variable that we started with, then you substitute again. You substitute v of x. Let me just say substitute v back into y. Now we must bring back y, therefore v is equal to y over x. I don't think I have to write any more step. You just have to substitute this, and then write here and say simplify. You are done, you have the answer. Right? You have the answer. Now to this it says simplify. It doesn't say make y subject of the equation. Again, I'm only saying simplify. I don't know what value you'll be getting as a function. Only as saying just try to simplify, then you will have the final answer after that. Okay. Yeah, so these are the steps that you have. Standard form first. So I must have a standard form first. Then the next thing you do, this is a substitution. So if you start with this in a standard form, which is actually what we suppose we must have, therefore you must perform this test in both m and the n, and then at the degree they must be the same. If this is the case, then you go for this step number 2 going forward. I know also, as I mentioned, depending on where you come from, so if the material you are using, they put it in this way, therefore it means your test, this is your test, and this t is 0 here, because as you can see, we're saying p is equal to, so is equal to q according to these conditions. So it means you're having t raised to p minus q, which is, they are both equal, therefore they give us a 0, therefore it's a unit. So that is why we only are seeing only f of xy there. So we can do the test in that way. I will mark it correct, I have no issues with it. And then when you start solving, we come into the same step. Then we solve together from number 2, going down to the final answer. Okay, so let us look at some example. Try to make some space. Okay, let us start here. Okay. Just serve exercises. Number 1. Again, the statement is simply just the same. Get the general solution. Find a particular solution where the conditions are given. Okay, so we are having dy over dx is equal to y cubed minus x cubed all over x y squared. They give us conditions is equal to 2. So how do we solve? Okay, so they give us in this way. I'll just go forward with it in this way. Okay. I'll not split differentials. You can do that if you want. Let me just face it. You are having f of, do my test here. Therefore, this whole right hand side is my f of xy. I'll just go ahead with it in this way. Therefore, I have a ty minus tx all over tx ty squared. Therefore, it's a t cube left with cube minus x cube all over t cube x y squared. You can see the t, they are same power, it's gone. Y cube minus x cube x y squared. What we see here is that f of tx, ty is equal to f of xy. To me, this implies I'm facing a homogeneous ODE. Then I start solving. When I solve, I have to substitute y is equal to v of x. The derivative there would give me v plus x dv over dx is equal to, where there is y, I put vx minus x cube all over x, where there is y, I put a vx. Then I continue from there. So therefore I'm having x cube is common, v cube minus 1 all over x cubed v squared. It appears the x cubed, they will cancel. Right, therefore now I'm having v plus x dv over dx. Therefore v cubed minus 1 v squared. Therefore means I'm having x dv over dx v cubed minus 1 minus that v would come here from left multiplied by v at the bottom all over v squared. So we're basically having v cubed minus 1 all over v squared minus the v from the left hand side. So you can see if we put this together, that gives us a v cubed minus 1 minus v cubed all over v squared. Okay, so this is what we did. Right. So what therefore means is that v cubed is gone with minus 1 over v squared. So we started with y and x. We now are having v and x, which is separatable. So we can separate the variables now. So therefore having v cubed is coming to join the dv side. You don't have to take the negative. We always say you just leave the constant aside. These coefficients, just ignore them. So we therefore have our minus is left here. It will be joined by 1 over x together with the dx. Therefore we're getting, this is power 2. So we're getting, we have to integrate here. We're getting a v cubed over 3 is equal to minus ln x plus a c. Okay, plus a c. So we now have a solution, but the solution is having a v, which is variable that we did not start with, so we must replace it with a y over x cubed. It's all over 3. I multiply all the times with the 3, therefore this will be minus 3 ln x. Supposed to be plus a 3c, but just a constant. This c is a big c. From minus to positive infinite, I'll just say c here. Right, just say c here. Then you can simplify a bit here. So this is a y cubed. How about I say plus 3 x cubed ln x is equal to c x cubed. Perfect. So this is our general solution for this problem. In fact, I think this problem will be enough. I don't think we need 2 exercises for this. The condition that we given was x1, y is 2. So we can try to get a c here. Let us use this version where c is already a standing alone variable. We can just make it subject of the equations from there. So c is equal to, I forgot. Let me check. Where is it now? I'm looking for the conditions. Oh, x is 1, y is 2. Okay. X is 1, y is 2. X is 1, y is 2. Okay, so it's simply just a 2. Okay, let me just leave it. Keep. Therefore, it's a plus 3 ln x is 1, so it means it's a 0, this thing here. C is equal to 8. Right? So therefore means we conclude that for our particular solution, here, so plus a 3 x cubed ln x is equal to 8 x cubed. Right. So it's simply just like that. So this is how you get a solution to a homogeneous differential equation. Okay. Really, I think this this one example is enough. You can do other exercises in our material, in our learner guide as well. You can always consult, of course. We have WhatsApp group, we have everything, we're always in touch. I say the recording now is, I think, is more than 30 minutes. So, okay, it's 31 minutes. I will stop here. Thanks.